or I sent everybody a message with the OneNote invite. Did y'all get it? How many have? Let me at least get, okay, good. Anybody not get an email from me? You didn't? See me after class, or did you just add this course?
Yes.
And you?
Yes, sir.
Okay, you need to see me. I want to make sure that I get this to you right after after class. Now, I don't follow the text per se. I'll give you some things out of the text. Like most professors, I just have things that I'm going to talk about, notes that I give you, and then I'll assign problems. Are you all able to see the problems? And if you scroll to the very bottom, there's the solutions, right? The real thing is the answer. The method that they use may not be a method that you're familiar with, because there's a lot of methods to solve problems. It's the final answer you worry about. And I gave you several problems, right? Did anybody have any questions about the problems? Seeing none? Now, if you don't like asking questions in public, send me an email or just see me after class. That's when my office hours. I'll be happy to help anybody with anything, okay? It's real important that you keep up. Last time we were getting through there, I had this problem. It was a little more complicated than you're used to seeing probably. And it required you to do like sort of reasoning at the second level. You had to use basic understanding to kind of go through and figure out what's going on down the road. Did you all follow me on this one, the last problem we were doing? It's easy to do once you spend a little time thinking about it, but your first exposure, sometimes you're not quite sure. Now I'm going to show you some things that will reduce your level of work, but it really is shortcuts that are very accurate. So let me go through this, and this is going to be voltage and current division. First is going to be voltage division. So what is that? Let me show it to you in a nutshell. Suppose we have a voltage source here, plus to minus V. I can call it Vs. Then I have a resistor R1, and I have some resistor R2. And I want to find the voltage here. Call it V out, or V2, better yet, V2. So how do I get that voltage? Well, that's the question. Probably at least half of you, more like 2/3 of you already kind of know just by looking how to do it. But some of you don't. So the first thing I'm going to say, if you ever are wondering where to start a problem, if you don't know how to get to the answer, start with what you know. You agree that these two resistors are in series. How many do? Series means they have to have the same current, right? Flowing through them. And if they are in series, can't we combine them down to just one resistance? You agree with that? It would be just a single resistance R1 plus R2. Do you agree with that? That means this current flowing here, according to Ohm's law, I can get by taking Vs over that single value, which would be R1 plus R2. Take a look at that. Do you all agree with that? I've combined it, R1 and R2, in my mind, sort of, put it up there, and made that statement. Do you all agree with me?
Yes, sir.
Now, if I have a current through anything, through any resistor, then this voltage can be gotten by taking that current through it times the resistor R2, right? You agree with me? Correct, class?
Yes, sir.
And if I multiply, just put in that value for I, so that means this is really the source voltage times R2 over R1 plus R2. Isn't that right? And really what I have there is something very interesting. It says the ratio of this voltage to the source voltage is just the ratio of the resistance that the voltage is, where you want the voltage, over the sum of the total resistances. Said another way, V2 over Vs is simply R2 over R2 plus R1. And that's voltage division in a nutshell. If you want the voltage across any resistor and you've got two in series, you just take the source voltage that's across both, multiply it by the resistance you want the voltage across, and divide it by the sum of the resistance. Y'all with me on this? How many have seen this before? You probably saw something like this in physics without ever labeling it, all right? It's a simple reasoning process if you think about it. This is voltage division. So let me expand this a little, make sure everybody can see it. What if I have this? This is sort of what the last problem I gave you required, some reasoning like this. Suppose I have an actual voltage of plus to minus 10 volts, right? And then I have a resistance of 20 ohms, have a resistance of 20 ohms, and have a resistance here of 60 ohms. So I've got 20, 20, and 60, and I want the voltage across this 60 ohm resistor. Just want the voltage. How would you get it?
On the current first.
Well, yeah, you could, but I'll tell you, there's even a quicker way. Some of you see it. You agree these two 20s could be thumped into 140? How many see that? Sure. So I get rid of that one. Make this 40. Now, do we agree we have two resistors in series with one voltage source? You agree with me, class? How many do? All right. So what do? We simply say that voltage is a source voltage, 10, multiplied by the resistance you want the voltage across, 60, over the sum of the two resistances, which is 100, or it's 6 volts. Y'all follow me on that? How many see that? It's not hard at all. And some of you will feel very, very confident that this is easy stuff. And that can get you in trouble, because sometimes you won't do the homework because it gets complicated in a hurry. Now, I'm going to tell you this. Do you remember I said the sum of the voltages around any closed loop was 0? You all remember that? Well, if I wanted the voltage here, I'll call it plus to minus V40. I could get it a lot of different ways. I know that somebody will say, well, we know the current, just multiply the current by 40 ohms, right? That's one way. Or we could say we can apply voltage division again. We'll just take 40 over 100 multiplied by 10. You all agree with that? That's another way. Or we could use what we know about the sum of the Kirchhoff's voltage law is what it's called. The sum of the voltages around any closed loop is 0. If I start here, I would get an increase of 10, right? If I start here, it's an increase. Do you all agree? I went from a negative to a positive. Here, it's a decrease minus V40. And here, it's going to be a decrease also, because the polarity, the way the current enters would be this way. That's where the positive polarity is, right? And we know that that voltage is 6, right? Correct? That would be volt using Kirchhoff's voltage laws to get that voltage. Some of you say that seems like more work than needed. You're right, but it still gives the same answer. Y'all see how it's all of them give an answer of 4. Correct, class? That's my point. Now, and are there any questions before I go on? Now I'm going to talk to you, that's Kirchhoff's voltage division, really. It's actually not Kirchhoff, it's just called voltage division. Next thing is going to be current division. Current division. Same idea. So here, what I'm going to do is show you the problem. I have plus to minus the voltage V. Then I'm going to have a resistor here, call it R1, and another resistor here, call it R2. And what I'm going to say is there's some total current flowing from here, call it I source. some of that current goes this way, call it I1, and some of it goes this way, call it I2. I'm just drawing this out so you've got a good picture in your mind of what I'm talking about. With me? All right. So, how many see that these two resistors are in parallel? How many see the voltage across them is V? Right? And therefore, I1 would be equal to just V source, or just V over R1. And I2 would be equal to V over R2, right? Y'all agree with that? And can y'all hear me okay?
Yes.
If you can't in the back, I will wear a mic, I'll do whatever I need to. Y'all with me on this one? All right, the total current is the sum of these. So I can say I source is equal to I1 plus I2, or it's V over 1 over R1 plus 1 over R2. Just take a look at that. I've just added I1 and I2, but I've decided to factor out the V. Right? Y'all agree with that? Now, what is the ratio of I1 over I source, or the total current flowing into both of them? Well, it's that, so it's V over R1 over V over 1 over R1 plus 1 over R2. I'm just rewriting. I'm getting the ratio of the current through I1 over the total current. Y'all see that? Some of you are going to say you're spending too much time doing the easy stuff, and you're right. Y'all see how the V's cancel? Because it's the same on both resistors, so the voltage is not going to play a factor in this. Now I have this, and what I'm going to do first is multiply both the top, the numerator, and the denominator by R1. In doing that, it gets rid of that, right? Makes that 1, and makes this R1 over R2, right? Y'all agree with, I'm trying to get to the point without spending a lot of time. Y'all agree it's nothing magical here. Now I multiply everything by R2. And when I do that, I get this. And lo and behold, now multiply by IS. I can see for current division, if I want the current through a component, well, I wanted I1, so I wanted the current through R1. It's really the source current, right, times the opposite resistance over the sum of the two. For voltage division, it was the actual resistor you wanted the voltage across, right? Here, it's the opposite resistance. Y'all see this, guys? All right, so that's current division, voltage division. Two things that are very important to understand because they allow you to solve problems very quickly. Now, for the homework problems, I gave you some. How many actually did them? And I'm not going to yell at you about it. All right, these things I'm just showing you, you'll make those that fast. All right, that fast to do them. Including the one I showed you last time, it would be done that fast if you think about it, right? Because we had the total current in that one leg, and if I wanted the current through one of those two resistors, I could use current division instead of doing the whole backwards envelope thing where I found the voltage first and then that, right? So I'm trying to tell you is these things are valuable and useful when I'm showing them. Now, after that, the next thing I show you are going to be some concepts with what's called grounded or ground. How many have heard the term grounded? It's a very common term. What it means essentially is that point is going to be assumed to have 0 voltage. So if I look at a circuit like this, and this is a typical type of thing, if I have 10 volts here, I have some resistor R1, some resistor R2 right here, and I have another voltage source, call that 20 volt. Nah, make it 5 volts here, and I put a resistor here, R3, like so. There's something that is very useful to do, especially if you use a voltmeter and you're reading a schematic and doing some things with, and trying to figure out where a problem lies. How many have used a voltmeter before? Good. All right, well, the voltmeter, you take one lead, the negative lead, and you put it at what's called the reference point or the ground. The symbol for ground we use, and this is really the zero voltage point. It's this symbol. It's one of three symbols. There's an earth ground, there's a chassis ground, and then there is something called I think it's called the circuit ground in your book, but I'm not sure. Grounds have this symbol. It'll be like that. It's 3 dashed lines. It means 0 volts. Now, I want to tell you, if you're looking at supplemental materials, sometimes for ground they'll use this. That is called an earth ground. All right. Sometimes they use this. That's a chassis ground. You don't have to worry about that. Earth ground is for if you ever are doing, actually the MEs might need this now that I think about it. If you're doing something that involves buildings and things like that, you have to have an earth ground, which is a big fat rod of metal that you pound into the ground, and it is connected to the earth, and it will short out current to the earth itself. It's a safety feature for lightning protection and things like that. That's really an earth ground in a nutshell, without getting into the complexity. This is a chassis ground. Y'all know the term chassis? Usually it's something that houses stuff. Metal boxes that have a lot of things in there are often grounded, and everything is referenced to that ground. You take your the negative terminal of your voltage meter, and you just use an alligator clip and clamp it to the chassis ground. Then you go around measuring the circuit, the voltages. That's what voltage is with respect to a chassis ground. This is a circuit ground. It means for an individual circuit by itself, on like a breadboard or something like this, that's the ground point that you would put your lead on the meter. That's the way I like to explain this because it's applications, all right? That's it, and they all fundamentally mean the same thing. If all the grounds had zero resistance leads to the other grounds, or zero resistance, there'd never be a voltage difference in them, but there is in the real world. There's a huge voltage difference, a significant voltage difference at least, for a lot of purposes between the earth ground and a circuit's ground that could be of the order of millivolts and even maybe tenths of volt, which becomes significant in a lot of ways that you'll see later. Okay, so for this, that's the reason we use a ground. It's the 0 volt point. Now, another thing about what I'm showing you is that allows us to do things without having a lot of extra numbers hanging around. You're going to see this. So from here, I like to talk about something called, first, Kirchhoff's voltage law is the sum of the voltages around any closed loop is 0, right? I mentioned that in the first study, right? The second one is Kirchhoff's current law. It's the sum of all the currents into a junction is 0. How many have heard of that? I'm not sure if physics teaches it or not. Maybe they do, but it's very important. So when I take a look at the sum, algebraic sum of all the currents into a junction equal to 0. What do I mean by that? This is what I mean. Suppose I have a junction, and I have I1, I have I2, I have I3, and I have I4. Now, the reason I'm doing it this way, think of current as an incompressible fluid, if you're an ME or an arrow. It means it's not like air where you can pressurize it and it can go through phase changes and it can be a whole lot of it or none of it. Anything flowing into this point has to flow out. You all follow me on that? That's what I'm getting at with this law. Algebraic sum of all the currents into a point is 0, or the way I like to say it, and the way I was taught, I believe, is whatever goes into comes out of. And I think in how many have had not incompressible fluid dynamics here? Or refrigeration? That's a term, they should have taught that law something like that, I think, the professors did, Birch and those guys did that. So really, when I look at this, whatever comes in comes out, I could say that I1 plus I2 plus I3 equals I4. You all see that? You have to have a direction for current. Just like you have to have a polarity for voltage. You all with me? And there has to be a reference. Good with that? So now, I'm going to go sort of move back a little for a second, remind you of something before we get to the next stuff. Remember when I had this resistor as such, R, I said if there was a plus to minus voltage V here, it would give rise to a current I that flowed into the positive terminal such that V, or really, let me do it this way, I times R is equal to V with the polarity shown. Do you all remember that? So now I'm going to use Kirchhoff's current law to show you how to solve these problems where all the voltages are referenced to ground. Now, I'll make sure I cover this thoroughly, all right? So first, if we're going to use Kirchhoff's current law to do this, the term for this in the book that you got a book that's for the course. It's called nodal analysis, but it's based on Kirchhoff's current law. You don't need to remember the term. And what it says is this: all the current into is the current out of any junction. Do y'all follow me? Now the way we apply this law is such. Remember I put that ground allowed me to get a zero reference, right? Now every voltage in the circuit will be measured with respect to that ground. Think of a meter. So here, I'm going to have some unknown voltage V. Y'all see that? My other two voltages on purpose were stated. Y'all see this, class? Matter of fact, what I'm going to do, I'm even going to make these resistors real numbers. That way it'll be even better. So I'm going to make this 10 ohms. I'm going to make this 50 ohms. And I'm going to make this 20 ohms. Okay? Those are going to be in the default there as ohms. I'll put the symbol in if it bothers. Can you read it in the back, guys? All right. So I've got that. And what my job is here, I'm going to find that unknown voltage. All right? I want to just see by analysis techniques I know what that voltage is. So here's how I do it using nodal analysis or Kirchhoff's current law. I said, well, the current here, I'm just going to arbitrarily call it I1. Doesn't matter what I call it. Doesn't matter the direction. And I'm going to call this current I2. And I'm going to call this current right here I3. The directions don't matter. You'll see. But you have to at least appreciate you need a direction for current. We're going to use Kirchhoff's current law or do nodal analysis. Now what I'm going to do is just write the obvious equation. Whatever goes into comes out of here. Y'all see that? So what's going into? It's I1, right? Plus I3. And what's coming out of? I2. You agree with that? Nothing deep here. I'm doing it on purpose this way so there's real numbers. Real numbers seem to stick with people. Maybe it's because they make a little more sense than abstractions. All right, whatever flows in, flows out, right? Now there was only one unknown voltage. It was this at that juncture, right? And that, by the way, is called a node. A node is where there is more than two paths for current to get it to. Here, I've got 1 and 1, right? But I got another one this way. There's 3, right? So there's more than one way to get out of this if you current flowing into it. That's a junction or a node. With me, class? Now, what is I1? Well, I1 would be the voltage on this side minus the voltage on this side divided by the resistance. How many understand that? Look over there. Whatever the voltage is on this side, this V right here if this was V1 and this was V2, then V itself would be V1 minus V2. Do y'all see that? If the voltage is measured with respect to ground. Y'all follow me on that, class? How many do? You good on that? All right. So when I come here, I1 would be the voltage on this side, and it's measured with respect to ground, so that's 10 volts, isn't it? Take a look, that's 0, that's an increase of 10. So it'd be 10 minus the voltage on this side, which would be, can you all see it?
V.
V, just V. Over R1. I made it a value, 10. Right? Plus I3. What is I3? Anyone? What's the voltage on this side?
5.
All right, so it's 5, right? And the voltage on this side, that's where the current's leaving.
V.
Just V. Divided by, that's true, 50, right? Correct? And that equals I2. What is I2? Anyone? Voltage on this side is?
V. V.
V. Voltage on this side?
0.
0. We don't have to do the 0. 0, who cares about 0? So it's just V over 20, right? Now that's one equation with one unknown, isn't it, guys? We can solve for V very easily, right? I want to tell you right now, if I just give this to you cold without showing you this, you'd have trouble. I promise you would. Unless you've had this course before or something like it. But now it should make sense to you. I'm using that ground to eliminate a lot of added stuff I have to carry on in equations to keep on reducing until I get to something manageable. Do y'all follow me on that? Now, with that, how do we solve this? I'm going to make a suggestion. I don't like fractions. First thing I do is multiply everything by 10. That gets rid of those little zeros, right? Then, yeah,
So with the ground, does that mean that there's no current going back into those?
ground has nothing to do with current. What does it have to do with the voltage? The voltage value, this entire thing down here, I'm going to color code this so you can see it. If you want to know where the 0 volt is, start at where it's 0, right there at the ground. Everything connected by that wire has got 0 volts.
Okay.
Nothing to do with current. Got me?
Sorry.
Just 0 volts. Now there's current's going to flow in and out of it, but you don't care about that. You just care about the potential.
Okay.
Now I come down here, so I multiplied everything by 10 first, right? Matter of fact, I can get rid of that. Now what do? Well, I could, what, multiply everything by 10 again, couldn't I? Y'all see that 5 times 2 is 10 would be the count. So if I multiply by 10, again, it would make this 5, right? By 10, make this 2. By 10, make that 100 minus 10V, right? Do you agree with that? I'm not trying to waste your time. I'm just trying to show you how easy it is. And I mean, if you like to do it a different way, it's fine with me. Then you can expand that, and I have 100 minus 10V plus, and this would be 10 minus 2V equal 5V, right? And then from here, what do? What would the easy way be? How about we leave the 100, let's see. So this is going to be 110 minus 5 is 105, right? That takes care of that, that, and that. And then equal to 12V. You agree with me?
No, it's
No.
5V.
What?
No, it's 5V.
Oh, I'm sorry, 5V. Not 5 volts, my bad. Thank you. So, my bad on this. Let's see. That's going to be 10 and 2 is going to be 7. So it's 12V on that side. You agree?
17.
Or, I'm sorry. Sorry, 12 on that side plus 5 is 17V. And then on this side, it's going to be 110. So 110 over 17 would be V. Thank you. You agree with me, everyone? And that's sort of how we get that doing something called nodal analysis. And I try to do it with real numbers. But we could adapt this to generalities and just call these values R1, R2, and R3, right? And we can make this V1 and V2, but you see the process. Do you all see this? And here's what it comes down to. The way you do this is first, if you have a junction or a node with an unknown voltage, you assign current directions. Now the way I always do it is I always go from left to right on the top part and from top to bottom. Now this is an exception because there's a voltage source there, but you can just as well go that way, all right? And then you would have I1 equal I2 plus I3, right? But the value of the voltages will be the same. And that's very simple. I'm looking at my watch, I got 132. Making a lot of racket over there. All right. That's how you do this. Now I want to show you something about adding voltage sources. We're going to do some problems, and I think doing problems really helps. So the next thing I want to show you is how do you go about dealing with multiple voltage sources if you're going to use Kirchhoff's voltage law. So if I have something like this, and I have a voltage source, Vs, then I have a resistance R1, another resistance R2, and another voltage here, plus to minus, I'll call this V1, V2, all right? I'm not putting a ground in this one. I'm just going to show you something, how to reduce the complexity. Now, remember I told you the sum of the voltages around any closed loop is 0, right? So first, you can see this is a single closed loop. All the things are in series. They have to have the same current. You all agree with that? If we take a look at this and we wanted to reduce complexity, here's what we can do. We start right here. I'm going to call this plus to minus VR1 plus to minus VR2. Now I'm going to start here, and if I sum these voltages, I get a voltage increase of V1. Y'all see that? Then I get a voltage decrease there, and another one. And finally another one. Now take a look. I hate to just use abstract numbers or abstract symbols, but y'all see what I've done there? Now one thing that's apparent, if this and this are real values, then when I look here, I really have a single voltage source that looks like it's V1 minus V2. How many see that? Polarized this way. And here's the way I'm going to explain it. Yes, sir?
Question.
Max, sorry.
No worries. Question, why would V2 not be added? Why is it subtracted?
Well, the sign, see there's a positive here, right? If I'm coming around here, anytime you go from a plus to a minus, I'm going clockwise when I sum voltages, it's an increase.
You mean a
So
negative
that-
to a plus?
Sorry.
You mean a minus to a plus?
Yeah, I'm sorry, a minus to a plus is an increase. Did I say that? I'm having a great day. I need some. Anyway, from here to here, it's an increase. So that's an increase of V1, then a decrease because I went from the plus to the minus. Now the only reason I would sign that way, I'm assuming the current will flow this way. And if it's wrong, the current will be negative. So there's going to be a decrease and then a decrease, two negatives, right? Now this one's another negative because I went from the plus to the minus. If they were reversed, it was minus plus, it would be added. And the thing about these you have to keep in mind, that value V2 could be minus 5. So then effectively, it's like switching these polarities and making a plus 5. Do you all follow me on that? Anybody ever measured the voltage potential on a car battery wrong, got a negative something? Oh, I do that all the time when I measure voltage. I get negative, and then the leads are wrong with something like that. Anyway, that's the same thing, but my point is, effectively what it looks like is this voltage is trying to push current around, This one is trying to go in the opposite direction, so the net effect is one voltage subtracts from the other. Do y'all follow me? So I can replace these two sources with one source. It doesn't matter where they're located in the actual circuit, it just matters their polarity. And replace this single voltage that I have here with V1 minus V2. And I hope that helps. Thank you. But I didn't bring that up clear. Yes, sir.
Is that the V2 gonna, is there any energy defect, like just this,
Talking about
disappears
power
in the environment?
dissipation? Huh?
Yeah. Does the power we're lost because the V2?
No, there's no, what he's getting at is something, we haven't talked about this, but I'm going to. He's saying, well, does it change any of the dynamics of the circuit in terms of power consumption or dissipation or anything like that?
Yeah.
It doesn't. This is electrically equivalent to what I had before. Exactly, in terms of dissipation or anything like that. Since you brought up the concept of energy and power, I'll go there next. But what I'm really trying to do is show you the concepts that are essential in a way that's meaningful and show you how to then give you problems where you can see it applied and you can hone your skills. Once you get confident doing problems, don't look at the solutions, just do them yourself, and you're banging them out left and right. Then you will have a high level of confidence when you take quizzes. You won't even blink. You'll be fine. Anyway, now what I'm going to do is this. When we talk about power, right? This is one thing engineering, it doesn't matter what you are. Aero, mechanical, electrical, industrial, fiber and polymer. You got a chemical in here, doesn't matter. Energy and power are the same to us. It has the same meaning. It's not shades of meaning or anything like that. Power is really something in watts. It has to do with usually a change of energy from either potential to kinetic or from electrical to thermal or something like that. Hair dryer takes electrical current voltages and changes it into a thermal heating, right? You add Q to the environment. There's all sorts of things like that, but energy, or I should say power is something you understand. And energy is really a time integration of the power of an event. That's all it is. So we talk about power with a resistor. So draw a resistor. As a matter of fact, the way your book will do it, if you own the book, it'll do this. It'll say power if there is a voltage across this black box, V, and there is a current into the positive lead, I, then the power, P, in watts, will be V times I, period. That's what it will say. So, if we take a look at something as simple as possible, I'm going to just put a voltage here of 5 volts, and I'm going to put a resistor here of 10 ohms. All right? When I take a look at that, I'm going to see I get a current here flowing this way. This would be a plus to minus voltage of 5 volts across it. I get a current I, and it would be what? 1/2 of an amp. Do you agree with me? It would be V over R, right? How many see this? In the back, can you guys, you with me on this one? I'm not trying to bore you. I really am trying to just make the point in a way that's hopefully meaningful. Now, if I have that, if I talk about the power associated with that resistor, right? Well, the current flowing in there is 1/2. Agreed? Into the positive terminal. Agreed with me? So it's 1/2. The voltage across it is 5. It means I have 5/2 of a watt. That's what power is in watts here. All right? BTUs and stuff, that's one thing I hated about thermo. I took ME thermo. We had steam tables, all the units were English. I don't know why in the world, but far be it from me to say anything too critical, so strip that from that. Anyway, that's the power. Y'all follow me? Now, in a circuit, something I didn't tell you is the total power associated with a circuit will be 0. So the power supplied is equal to the power dissipated. You all follow me? Now look over here to this element. Well, the power associated with that source, the voltage source is 5, right? But notice the current is entering the negative terminal. Do you all see that? It's coming out the positive. It's a source. It's creating current by probably electrochemical reaction. It's forcing current out the positively. Do y'all follow me? It's a pressure head. So it's times minus 1/2. That's the current. And that means that it's going to be minus 5 amps of watts. And the sum of the two is equal to 0, isn't it? Now that's an old way of checking things. If you go around and you got multiple sources, multiple resistances, if you take the power associated with each element and add them up, it will come out to be 0 if you've done everything right. And if it doesn't, you've done something wrong. And the truth is, if the current's going into the negative, coming out of the positive, it's negative power. If it's dissipating power, it's positive power. I know that doesn't jive with everybody. You're thinking, well, wait a second, creation of power should be positive. I didn't write the rules for this, I'm just telling you what they are, okay?
So it's like the opposite of voltage, kind of, like the sign is different.
No, I mean power, this is, I think I know what you're trying to say, but power is something that when it's dissipated, it's positive. When it goes, when literally a resistor dissipates power, it turns it into heat, usually thermalizes it or photons. It's positive. Negative power is associated with a source. That's something that's giving power to the system. Got me on that? Like a battery or a generator. I hope that makes sense to you. You know, that's the big deal. You have to make sure that creation power or a source will have a negative. But a source can also dissipate power. If you're charging a battery, you're putting current in through the positive terminal, so it can act like a resistor. All right. That's power. Energy, by the way, I don't need to get into that now. It would just be a time integration of the power over time, but I don't worry that much about that. So there's one thing I want to do. Since I got you here, got you kind of.
Excuse me, sir.
Go ahead.
So in the previous diagram, you said V1 minus VR1 minus VR2 minus V2 equals 0. So how you assume that current flow from V1 to the V2? Like is
Why
the
did I assume it?
because
that's
the
an
V1
arbitrary.
bigger than the V2?
I can assume, when I do this, I did it in my mind, but you can assume current in any direction. Now, the final value of current, if it was assumed in the, let's just call it wrong direction, it would have a negative value. It will always come out in the wash, and you'll see that. So the next thing we're gonna do is a problem. You're gonna do it with me, okay? Here's the problem. I have a voltage source. Make it 20 volts. We'll see how far we get on this. I have a resistor of 10 ohms. I'm going to put a resistor here of 100 ohms. And then, let's see, make this 100 ohms. Make this 50 ohms. And make this 40 volts. All right? And I want you to tell me what the current is through this 100 ohm resistance. All right, there's a question. Now, there is no one simple formula you can use to get at it. You've got to think about the tools I gave you. Now listen to me. So, when you see something like this and are wondering exactly where to start, go with what you know. Remember I told you about the grounds? A ground, I always put at the low connecting point, I call it, down here. Why? Because it's 0 volts, right? It's 0 volts, give me 1 second. And I know from just my, can you come up here and press this thing shut, or cancel, just come up here and hit cancel. See the cancel button? Just press it. Thank you. The bomb goes off all the time. Go ahead.
So, if there isn't a ground already stated in the circuit, we
You can put it in. It is, you can do this. This is the nice thing I didn't tell you, but if you need a ground, you can put one in, which is nice. Remember, it's just a reference. It says if a guy's coming here and troubleshooting, or if you're troubleshooting, that's the point where you clip your negative lead. Think of it that way, and it'll make more sense, all right? Makes life easy. That's the reason we use a ground. So that's 0 volts. I put that on there first, right? Now, every voltage in the circuit, here, 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 will be measured with respect to that ground. Make sense?
Yes, sir.
Okay? Now, do I know what this voltage is on this portion of the circuit with respect to ground?
20.
Absolutely, 20, right? Same with this portion, it's 40, right? But the point I don't know the voltage with respect to the ground at is right here, correct, class? And I'm using this color coding method. If you want to know where the voltage is the same, if you take a marker or a dark, or any kind of a colored marker, and just start at one end of any component and move through all the connecting wires until you can't go any further, that has the same electrical potential, right? And anytime you have the same two colors across any two components, they're in parallel. That's the nice thing about, if you ever want, when they teach you how to do circuit redraws years ago, they say get some colored markers and we're going to do them. Because some people come up with bizarre ways of showing resistances in the circuits. Anyway, what's the one voltage I don't know? Right here, right? So you need a voltage, put it in. Agree? Now remember, I asked for this current, but I'm not going for the current. I'm going for something I know. Do y'all know how to get that voltage? I'm only worried about the voltage. How would you do it? There's one key thing I'm looking for. Remember, forget about that current. I know if I have that voltage, can I get this current? What would it be? Say that again?
V equals IR.
Well, it would be what? That current would be V over 100, right? If I knew the V, I got the current. Y'all agree with me? So let's go get the V. How would I get it? There's one thing I would do to this circuit.
Nodal analysis?
Wait a second.
Nodal analysis?
Yeah, but there's, I'm trying to.
Parallel resistors?
How about those two in parallel? You agree? What could I replace them with? 50, right? Take the 1, divide by 2. Correct, class? So let's make it 50. We'll worry about I in a second. Now I'm fighting the clock, right? 50 ohms. Now if I do that, can I get it? This sure looks similar to something we saw moments ago, right? Now what would I do? I would call this some current. I'm calling I1 because I'm running out of time. I'd call this some current, I2. And if you want to, we can go this way. We can call that I3. Agreed? Sorry, I'm not trying to fly, but y'all follow me? Y'all, it should look similar. It should look exactly like, we only want to get V to get I, isn't that right? We get V, we got I. So then we write the law. I1, right, equals I2 plus I3. We're getting there, correct? Let's write it down. This is not, I mean, believe me, this is, I shouldn't say rocket science because there's arrows in here. You guys are rocket scientists. You agree with me? All right, now how do I get I1? Anyone? Remember what I did? Voltage on the side the current's going into would be plus, right? Minus voltage on the side the current's leaving, divided by 10, right? How many see that? If you have a question, you can ask me if I'm not clear. It's okay if you don't worry about it. All right. The real thing is I'm saying we're using these voltages for one reason, to get the currents, aren't we? So the voltage difference across that resistor driving the current would be the voltage on this side minus that side, right? The voltage on that side divided by the resistance. Yes?
How do you know the direction of I3?
I arbitrarily put it that way. I can make it any direction I want, but then what? I3 here would be the voltage on this side plus V minus the voltage on this side, 40 divided by R, right? It could be negative, doesn't matter. It comes out in the wash. You okay with that? Let's just do this. So what's I1?
20 minus V
So it's 20, you're right.
over
20 minus over equal. What's I2? You're right.
V over 50.
Right, V over 50, right? And what's I3?
40 minus,
Not-
or 50 minus.
V minus
V minus
40,
50.
right? Because there's the word current's entering, right? It's V minus, right? V minus 40 over 50. Y'all see that, class? Make sure you get the polarities right. Now from here, I got one equation, one unknown. I'm not gonna bore you, but I multiply both sides by 50 myself, then I'd solve, okay? That's the way you do these problems. And by the way, almost everything you're gonna see here is perfectly logical. There's nothing coming at you where, you know, and then there's the Schrodinger equation and we get quantum levels. We're not gonna do that. Anybody ever have quantum dynamics or quantum